This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Wind resources will make a significant contribution to our renewable energy future. With that future as a background, UC San Diego was funded by the National Science Foundation to conduct on-site and full-scale seismic tests of wind turbines. Under the guidance of Principal Investigator Ahmed El-Gamel, the testing program is part of a comprehensive study to understand the structural response of wind turbines to seismic ground shaking. Ahmed El-Gamel shares his insights about the project.
Wind turbines in California are on their way to increase by more than tenfold in a few years, and they're getting bigger and bigger. Here at UCSD, we have a shake table that is an outdoor shake table where you can put any size wind turbine and shake it, and so the right equipment and the right time for looking at these systems really coalesced, and we went for it. The team of researchers on this project included Professor Xiaoming Wang, who is our steel expert on the project, Professor Enrique Lucu with expertise in earthquake engineering, and Professor Joel Conti with expertise in reliability. With the combination of all this expertise, we were able to do the earthquake engineering part, do our studies related to the resilience of the steel tower and its ability to handle the applied loads, and also take all this information and translate it into outcomes as to the level of risk that might be associated with a wind farm existing in earthquake country. So wind turbines are this special structure with much of their mass all the way up on top, very far from the ground level. When the waves come from the earthquake, they shake the base, and then this motion is amplified many times over as it climbs all the way to the top of the turbine where the mass is. And mass times acceleration from the earthquake is force. Having a point force like this all the way up on top of the tower causes very large bending stresses in the turbine tower and, of course, on the foundation of the turbine. From a distance, it looks like the wind turbine is a simple structure in that it's a large mass on top of a pole, and this is how it vibrates. But as you look closer at this system, you find that part of this large mass is in constant rotation because the blades are rotating all the time due to the wind acting on them. In addition, the interaction of the blades with the wind causes damping to appear from aerodynamics, which is also a component that affects the vibration of the turbine during an earthquake. So in addition to that simple structure that looks like just a point mass on a pole, you have aerodynamics to deal with, and you have a large portion of the mass in rotation. Typically in our area of work, in buildings and so forth, the structure is not moving. And when the earthquake comes, it shakes a structure that is static before the earthquake. And looking at this problem where we have a large portion of the structure in rotation, coupling this pattern of motion with the motion from the earthquake is scientifically an interesting aspect that has not been looked at before. In addition, the rotation also engages the aerodynamics and implications of the aerodynamic damping and other effects into the picture. And then we end up scientifically with an extremely interesting problem that we typically don't look at when we're looking at just the response of a typical 10-story or 20-story building. So the project aimed to look at various stages of the wind turbine response, including the state where it's not rotating and just how it behaves as a simple structure. And then from there, taking it to the situation where there is rotation and where there is aerodynamic interaction. There is no data of that type anywhere. And to do this, we went out to large, modern operating wind turbines, and we recorded their vibrational characteristics as they are working. And we also had this component of getting an actual but smaller utility scale wind turbine and placing it on the outdoor shake table and subjecting it to earthquake motions exactly like the ones that have been recorded in previous earthquakes in California.
The operating wind farm, as well as the turbine for shake table testing, were provided by the principal partner in the project, Oak Creek Energy Systems, one of the most successful and innovative wind energy producers in California. Ed Duggan, Vice President of Oak Creek Energy Systems, comments on some of the reasons for supporting this research.
California is a very seismically active state, and you know, renewable energy has been identified as an important part of the energy plan for California and for the country. As these turbines get bigger, it's clear that we need to be prepared for the sort of seismic events that we might see here in California.
Hal Romanowitz, President and Chief Operating Officer of Oak Creek, comments on why the project is important for the future of wind turbines.
As we go taller yet with the turbines, and that's going to happen while you see 80-meter hub heights now, turbine hub heights of 150 to 180 meters are being designed. And so if we're going to have wind turbines be increasingly productive and efficient in the future, it's absolutely crucial that we have structurals that are competent for the earthquake conditions. Because as you build projects, you can't be thinking then about, gee, are we good enough? We have to prove now what's necessary to make a project last.
The field observations were conducted at Oak Creek Energy Systems wind farm in Tehachapi, an unparalleled resource for California. Ed and Hal explained the unique nature and unequaled potential of the Tehachapi area.
Tehachapi is a pretty unique place, and the uniqueness of this place is why we have all these wind turbines here. First of all, we have the Sierra Mountains that run to the north of us, and the Tehachapi Mountains that run to the west of us. So there's a pass in between these two chains of mountains, which is called the Tehachapi Pass. That is enhanced by the fact that we have prevailing winds that come off the ocean and go down the San Joaquin Valley and then get funneled up into the Tehachapi Pass. And then the last thing that really enhances it is we have the desert off here to the east, which heats up to a large degree every day and basically creates kind of a low pressure gradient out to our east, which kind of enhances the flow through the pass. So we get very, very predictable winds here.
Because of the effect of all of these things, Tehachapi has been one of the better, more reliable wind resources in the United States. And Tehachapi accounts for 40% of the entire plausible wind resource of the state of California. It's a huge percentage of the state wind resource right here. Tehachapi is going to be probably the single largest wind resource area in the country. In a compact regional area, there's going to be probably more energy generated out of Tehachapi than any other comparable sized area in the country. Currently planned for about 2,900 to 3,000 megawatts. Again, huge. That's the size of 3 nuclear power plants. So there's a lot of clean wind energy right here in this area utilizing this resource.
The whole Tehachapi area currently has about 900 megawatts of installed capacity, which is enough for the annual needs of something on the order of 250,000 homes. And that nameplate in this next year will nearly double. So we'll be making a peak output of somewhere around 1,600 megawatts and enough energy for over 500,000 homes here, just from Tehachapi, which is only one of the major wind areas here in California. It's expected that over the next 10 years, that will double again. So you're talking about enough energy from this area for over 1 million homes.
Amidst this unique resource, the researchers conducted their field observations. Ahmed El Gamal comments on the purpose of the observations, which were organized and conducted by his graduate student researcher, Jan Prowl.
When we started, we wanted to document as much meaningful information as possible. So there was information to be gathered and documented about the dynamic characteristics and response characteristics of large modern turbines that are available and operating today in wind farms across the country. So a big portion of what we did was to go out and measure the dynamic characteristics and the salient response mechanisms associated with these turbines in their native environment as they are rotating.
Out in the field at Oak Creek Energy Systems, we were looking at large modern turbines in place, so a 900 kilowatt turbine and 1.5 megawatt turbine, which represent what's really in use throughout the US right now. And we were characterizing the dynamic properties of those turbines. By doing that, it allowed us to, one, help understand if simulation tools were properly predicting those characteristics. And it also helped us tie together our shake table tests on the smaller turbine, the 65 kilowatt turbine, which still is a very large structure, almost 7 stories tall, or actually beyond that if you include the blades, and take those results and understand how those results and characteristics change as you get into these larger turbines, which are 20, 30, 40 stories tall. What we did was called ambient vibration testing, and so under wind loading or just micro tremors, maybe a truck driving by, any structure vibrates a little bit, and with high quality instrumentation that the NSF has funded, we were able to capture those vibrations and by careful analysis translate that into the characteristics of the structure and get very accurate results on how the structure is vibrating, how the structure is dissipating energy, and how that changes depending on whether it's operating, depending on the wind speed and other factors. So we instrumented the tower at various elevations. We put accelerometers to look at the vibration in the tower. We also instrumented accelerometers at the ground level on the turbine's foundation and in the soil surrounding the turbine. That allowed us to understand the influence of the actual soil and foundation system on the turbine. By looking at the response at the ground level, we could decouple the vibration in the soil and the foundation from the actual vibrations in the turbine. And so we were able to understand how soil structure interaction affects the response of the turbine. We're able to quantify that. Also, we attach what's called an eccentric mass shaker, so that input a narrow band force at a fixed frequency to the turbine tower. And by doing that, we were able to get very good information on how the turbine responds at those particular frequencies, further improving our results on understanding the resonances or natural frequencies of the turbine. When we record the data from the accelerometers, all of the accelerometers are very carefully time synchronized, and so we know exactly what's happening at an instant in time throughout the tower, on the foundation, and throughout the soil. By looking at that and understanding either in the force vibration case the frequency that we were imparting shaking to the turbine, or in the ambient vibration case by carefully looking at those characteristics and stepping through algorithms to analyze that, we can then understand very specifically how the turbine was responding. We have visualizations showing the mode shapes and natural frequencies of the turbine. What you're seeing here is basically the shape that a structure wants to vibrate at a particular rate. And so at lower frequencies, you have what's called the primary mode, which tends to be a very simple shape. And as you get to higher frequencies or more rapid vibrations, the shapes progressively get more complex. And we also use those results to show that the computer models that we have to reproduce the behavior of the turbine are similar to what we're actually observing in a real turbine.
After gathering the field data at Tehachapi, the team constructed a full-scale turbine on the NIES UC San Diego outdoor shake table at the Englekirk Structural Engineering Center. As in any wind turbine construction, first the tower segments were erected. Then the nacelle, housing the generator, was hoisted and attached to the tower. Finally, the turbine blades were hoisted and affixed to the hub of the generator. The turbine tower and all its components were thoroughly instrumented to record strains, displacements, and accelerations that describe the tower's response to seismic motions. Jan describes the test's protocols and objectives.
In testing on the shake table, we first tested the turbine in one orientation where the shaking was perpendicular to the axis of rotation for the rotor, and in that configuration we conducted tests where the turbine was parked or not moving, and tests where the turbine was actually spinning in the wind. Then, after those tests were completed, we rotated the turbine 90 degrees so that the orientation of shaking was actually along the axis of rotation of the rotor. And so there again we conducted tests where it was parked or not rotating, and tests where the turbine was rotating in the wind to quantify the importance of each of those variables in the response of the turbine to earthquake shaking. All the earthquakes that we used on the shake table were from actual recordings of earthquakes out in the field. Initially, again, low-level tests, but as we stepped up the earthquakes to higher level, we achieved almost an in excess of 1 G of acceleration. That's very strong, but that has been recorded. For instance, in earthquakes like the Northridge earthquake or the Kobe earthquake, we've seen accelerations like that in actual earthquake recordings. Basically, in that situation, if you were standing on the table, you would not have been able to stay standing up. And in pretty much all the cases, we see fairly significant amplification in the turbine. So for example, when we had an input acceleration of up to 1 G, at the top of the turbine, there was a response of 3 G. So that means almost 3 times the weight of the turbine was acting horizontally, and the tower actually had to resist that without collapsing. The tower was actually working harder to resist that earthquake load, that horizontal load, than to actually support the turbine in response to gravity.
While at the extremes of shaking, the tests showed the response of the tower to high G forces, other data clearly revealed the unique effects that occur due to the nature of the turbine's operation.
So to allow us to isolate influence of different components, we replayed the same earthquake for when the turbine was parked and then when the turbine was operating. So as you'd expect, when the turbine was parked, before the earthquake started shaking, there really isn't any vibration in the turbine. But when the earthquake started, the turbine started to vibrate. And like you'd expect from a structure that has low damping or really not much ability to dissipate energy, you see a very clear, very clean response to the turbine, and it's prolonged. It continues for over a minute, even after the earthquake shaking stops. But in the case where the turbine is operating, there's vibration from the blades rotating, from the gearbox, from other sources in the turbine. And so if you look at the response of the turbine, it's shaking even before there is earthquake shaking, and that's apparent. But as the earthquake shaking starts, it becomes strong enough to overpower that vibration from the operation. In comparison to the situation where the turbine was parked, there's actually much higher damping. And so that response from the earthquake dies out much quicker, maybe 5 or 10 seconds after the earthquake is over. And then you return back to that initial vibration where it's just vibrating in response to the blades rotating, to the gearbox vibration, and so forth. You actually have large blades flapping in the wind, and that flapping causes what's known as aerodynamic damping. So you're taking energy that normally would need to be dissipated in the turbine vibration and actually transferring that out into the wind. And so the turbine stops vibrating, or damps out more quickly than you might expect. Following the shake table test, we were able to construct models of the blades that describe the blade in terms of its stiffness, its mass distribution, also its aerodynamic properties. And so when we run those simulations, we actually see very good agreement between the amount of energy that was transferred into the wind in the experiment and the numerical simulation. So our results show a very consistent response, both in the model, in the computer, and also on the shake table.
After completing full-scale shake tests without failing the tower structure, the team then explored the limits of the tower's performance by conducting static testing at UC San Diego's Charles Lee Powell Laboratory. Ahmed El Gamal explains.
The third phase of our work was to assess the capacity of the turbine tower to resist moments that are applied on it when the earthquake hits. And for that, we also did a phase where we applied a force on the very tip top of the wind turbine tower all the way till we were able to document the mechanism of deformation of this tower. And the good news there was that we found that these towers do have a certain level of ductility after they sustain minor damage, which allows them to be repaired quickly if needed without necessarily suffering any catastrophic damage or total failure.
After months involving field observations, numerical analysis and modeling, full-scale shaking, and static tests, the research yielded promising initial results for the present state-of-the-art in wind turbines.
As we expected, the expected response of a turbine at a particular location under a certain earthquake excitation is highly dependent on the nature of the motion that occurs at this location and also on the dynamic characteristics of that particular wind turbine. But overall, we are finding that wind turbine towers do appear to have quite a bit of reserve strength. And so we're not too concerned at this point that in any coming moderate earthquake or even somewhat strong earthquake that necessarily we expect to see much damage at all. And that's good news.
We're finding that existing turbine designs include a reasonable amount of conservatism and are likely well suited for earthquakes. We don't see any impending disasters or just complete inappropriate designs out there.
We made a pretty strong effort to cause a failure and then we couldn't do it. So I would say that's a pretty encouraging sign for our industry, that the turbines are pretty strong and should be able to withstand it. And I think we just want to make sure that as they get bigger, we don't miss something and have disasters happen.
But more importantly, beyond these initial results, invaluable new information has been gained that will make significant contributions to the future of wind energy.
The data is going to be used to refine guidelines and also to be part of frameworks for risk assessment and overall system reliability. And so these are the main purposes eventually of the data that we have gathered.
It's extremely important that the risks of this development are understood and that people can feel good about investing in wind energy in places like California.
In the end, you want more reliable, more efficient projects that produce a lower cost of energy. And while wind is one of the most cost-effective energy sources now, it's going to get even significantly better.